Hello and welcome back to C++ real-time audio programming with Bela. I'm Andrew McPherson, one of the original creators of Bela, and in this course we look at a number of different music and audio topics related to synths and audio effects, and we associate each of these topics with one or more C++ programming topics. Specifically today, we are going to look at controlling the parameters of your real-time audio project, and we're going to see this in the context of building oscillators and wavetables. So over the course of this lecture, you will learn how to use Bela's browser-based GUI as a way of controlling the projects that are running on your Bela board. We're also going to look at linear and logarithmic ranges for parameters and how to rescale them. In the course of this lecture, you'll make an audio generator that has multiple oscillators slightly detuned from one another, which is a common technique in modular synthesis to produce a richer sound. You can find companion materials for this lecture, including code examples, at the GitHub link at the bottom of the screen. To follow along with the code examples, you'll need a Bela kit, which can be either a Bela starter kit or a Bela mini starter kit. For some of the lectures, though not this one, you'll also need some standard electronic components. More details can be found on the GitHub page, and it's worth looking at this now because we're going to need some of these components in a couple lectures. Also, if you're just joining us, be sure that you've updated your Bela software to the latest version. You can find this at learn.bela.io/update. You will need the latest version of Bela to ensure that you can run the code examples for today. Let's just start with a brief review of the oscillators that we've built thus far. In Lecture 1, we made a real-time sine oscillator that generated the waveform one block at a time. And we saw that to do this, we had to keep track of the phase of the oscillator from one block to the next. Now, as you recall, the phase is the argument to the sine function. It can take a value between 0 and 2 pi, and the analogy was to the y-coordinate of a particular angle on the unit circle. And so, given this definition of phase, we had to figure out what we meant by frequency. And what we saw in Lecture 1 is that the frequency of the sine oscillator was essentially how fast we would spin around the circle. In other words, it was the derivative of the phase. So looking back to how we generated a real-time sine wave, what we did was remember the phase between each call to render, and after every audio frame, we would update the phase according to a particular formula that we see here. If phi represents the phase, then we would calculate phi equals phi plus 2 pi f divided by fs, where f is the frequency of the oscillator and fs is the sampling frequency, in this case 44,100 Hz. For more details on how that works and the code that implements it, go back to Lecture 1 in this series. Then in Lecture 3, we looked at how to build an oscillator using a wavetable. The difference here is rather than calculating the value of the oscillator mathematically, we would look it up from a pre-stored table of values. And we saw in this lecture that the table could conceivably hold any wave shape and not just a sine. We also saw in this lecture how we could use linear interpolation to get a higher quality sound output from the same length of table. Moving from a sine oscillator to a wavetable oscillator, one of our challenges was to figure out how to manage the frequency. As we saw in Lecture 3, for the wavetable we were keeping track of a read pointer. The read pointer basically told us where within the buffer we were reading from at any given time, and it was essentially an analogy to the phase of the oscillator. So whereas in the sine oscillator we were spinning around the unit circle, in the wavetable oscillator we were reading from the beginning to the end of a buffer, more or less like this. The question that we asked ourselves was, if the read pointer corresponds to the phase of the oscillator, then how do we determine the frequency of our wavetable oscillator? And we saw in the sine oscillator that the frequency was the derivative or the rate of change of the phase, and therefore, in the wavetable oscillator, the frequency was given by the rate of change of the read pointer, or in other words, how much we added to the read pointer on each successive audio frame. So that's some background context. In this lecture, we're going to look at how we control the frequency of the oscillator. There are, of course, many ways to do this, but we're going to focus on a particular capability of the Bela platform, which lets us make browser-based GUIs that send parameters to the project running on the board. The place to start is with the example called Sine Slider, which you can download from the companion materials at the link here. Upload this project onto the board by dragging the zip file into the browser window. It should prompt you to create a new project. Once you've done that, you can click the Run button in the lower left-hand corner of the browser window, and once the project is running, click the GUI button, which looks like a set of sliders. When you do that, you'll see the GUI pop up in your browser, and you should be able to adjust the frequency and the amplitude of the oscillator by manipulating these sliders. So here I have that project running, and I can open the GUI by clicking on this button here, and we see that we get a set of sliders, one controlling the frequency and one controlling the amplitude. And there we have it. If for any reason you don't see this GUI, then check that you have the latest version of the Bela software. Let's look briefly at the code that you need to implement a GUI like this in your project. There's a few things you need to do. This set of sliders requires that you include a couple libraries in your project, so you should include GUI.h and GUIController.h in your file render.cpp. This then lets you create a couple objects, one of type GUI and one of type GUIController. Now, what's really convenient about this particular GUI library is that you don't need to write any external files to define what your GUI looks like. All you need to do is inside your setup function, tell the system what controls you want to create, what they're called, and what their ranges are, and it will create the sliders for you. So in this particular example, we have two sliders. The first one is called frequency, and the second one is called amplitude. And you can see that we can specify a default value for the parameter, a minimum and maximum for their range, and an increment value, which we'll talk about later in this lecture. Then once you've created the GUI, you can get the parameters from within your render function. Notice that how I'm doing this is with the method called controller.getSliderValue, and what I'm passing in is the index of the slider that I want to read. This corresponds to the order in which you created them. Notice here that I'm storing the results in these variables called frequency and amplitude, but these are no longer global variables as they were in the previous lectures. Ask yourself why this still works. Another difference from previous projects is that we are querying these sliders once per block, and not once every frame within the for loop right below it. Why would this be? The reason is that Bela is a hard real-time system, and your render function is guaranteed to be the highest priority task on the board. What that means is that when your render function is running, nothing else on the board is running during that time. That includes any code that would communicate with the browser-based GUI. So what that means is that when the render function starts, we know that there's no way for the sliders to change value until the render function finishes, because the code that would monitor the sliders simply can't run. Therefore, it's safe to gather the value of the sliders once at the beginning of the render function and use that for the duration of that block. So that's it. That's all you need to do to use the browser-based sliders to control values of your project on Bela. Let's now turn our attention to the nature of the parameters themselves and how we can adjust their ranges. It's a very common situation that we'll have some parameter that we have read that has one range, and that we want to rescale that parameter to cover a different range. For example, a number of controls that we might use might have a range between 0 and 1. This is true of Bela's analog inputs, for example. But we might want to use that 0 to 1 range to cover a different range of numbers, for example, adjusting the frequency of an oscillator. There are mathematical expressions that you can use to perform linear rescaling from one range of values to another. And Bela provides a convenient function to do this for you. It's called map, and you can see the code to do that right here. The map function implements this equation, where x is our input value, y is our output value, xmin and xmax are our input range, and ymin and ymax are our output range. This is the equation for linear rescaling of a parameter. Let's take a visual analogy. Suppose that we had a line that was plotted between the points xmin, ymin, and xmax, ymax. If we had an input value x and we wanted to figure out what output value y corresponded to it, all we need to do is look up where x maps to on this line. And in fact, if the value of x is outside the range that we have specified, for example, if it's less than xmin or greater than xmax, this function will still work and it'll simply extrapolate the values like this. So why don't you try this now? In the sine slider example, try using the map function to remap the range of frequencies. Instead of being from 220 to 880, map it to some other sort of range, for example 110 to 440. Pause the video here, give that a try, and then we'll look at it. Okay, here we are in our sine slider code, and you can see that we have this variable called frequency, which we read from the slider, and it has a range between 220 and 880 with a default value of 440. Now what we want to do is remap this to be a different range, say 110 to 440. Now of course we could just change the numbers here and that would work just as easily, but this is a good example of how to use the map function. So let's write it here. Frequency is equal to map, that's our function, and if you recall from the slide, map takes 5 arguments. The first one is what the value is that we want to remap. So that is, again, this variable called frequency. And then we need to provide the input range. So this is from 220 to 880, and then finally the output range, which I said is going to be from 110 to 440. And you should find now, if you run this code, that although the numbers that are displayed in the GUI don't change, we're going to have a sound that is an octave lower than it was before. So that's the map function, a really useful tool that will come up in a lot of different contexts. There's another common function that you'll often see in working with the ranges of parameters, and that is called constrain. What constrain does is pretty simple. It just clips the value of an input x to stay within a specified minimum to maximum range. So any value within that range will be unchanged. If it goes below the minimum, it will just return the minimum. If it goes above the maximum, it will return the maximum. So you'll often see this used in your projects as well. As we discussed, the map function performs what we call linear rescaling. It's important to emphasize that although linear rescaling is easy to do, it's often not the best perceptual way to go about manipulating your parameters. For example, the perceived loudness of a sound is actually logarithmic to its actual raw amplitude, and this has to do with a number of factors both related to physics and related to human physiology. But the point for us is, if we want to make a parameter that manipulates the loudness of a sound, we may want to do that on a logarithmic rather than a linear scale. And there's a scale which is ready-made for exactly this, which is called the decibel scale. It goes like this. For a given ratio between two quantities, given as A, we could convert this back and forth between a decibel scale and a linear scale according to these equations. So A in decibels is given as 20 times log base 10 of the linear ratio, or equivalently, the linear ratio is given as 10 to the power of decibels divided by 20. Now this may seem a little bit obscure, so maybe it's helpful to explain where this comes from. The word decibel is literally a tenth of a bell, and a bell is a unit of measure named after Bell telephone in the very early days of the telephone system. The idea at the time was that the bell could be used to express the ratio of signal loss over long telephone lines. But it quickly became clear that 1 bell was a relatively crude metric for practical situations, and that the decibel was a unit that was much closer to the situations we practically encounter. In certain situations, for example sound pressure level in acoustics, you'll see decibels expressed as a 10 log 10 scale, i.e. 10 times the log base 10 of the linear value. Notice that here we have 20 times the log base 10 of the linear value. The reason for this is a bit more complex, and it has to do with measuring power versus measuring signal amplitude. We're not going to go into it here, but just perhaps take it as a given that we can use these formulas to convert back and forth between signal amplitude in decibels and signal amplitude in linear terms. To take some examples, a ratio of 0.1 or 1/10 could be written as minus 20 dB, and convince yourself that that works both ways around in these formulas. What then, for example, would be 0.01 in dB? Well, 0.01 is 10 to the minus 2, so log base 10 of 0.01 is negative 2. 20 times negative 2 is minus 40, so this is minus 40 dB. What then would be plus 60 dB as a linear ratio? Well, we could take 10 to the power of 60 divided by 20, that's 10 to the power of 3, that's 1,000, and so forth. Now, I want to emphasize that the decibel scale is about ratios between quantities. So, in every case where we use dBs, we should always be asking, dBs relative to what? And there's lots of different answers to this question. In digital signal processing, we'll often use a term called dBFS, which stands for decibels full scale. What we're saying is, by definition, 1.0 is defined to be 0 dB full scale. So smaller values would have negative decibel numbers, and larger values would have positive decibel numbers. And this is probably the most common case of decibels that you will see if no other particular suffix has been specified. We'll also see decibels used in a lot of analog systems, and there we'll see scales like dBV, where the V stands for volts. There, 0 dBV corresponds to 1 volt, smaller decibel numbers correspond to a lower voltage, positive numbers to a higher voltage. We'll also see the scale dBu, which has to do with 1 milliwatt of power into a standard 600 ohm load. This is a very particular audio-related scale that you'll often see, especially in pro audio, in defining signal levels. As we discussed before, you'll also see dB used in acoustics, for example for sound pressure levels, where it's going to be a 10 log scale rather than a 20 log scale, and this has to do with the fact that it's measuring signal power rather than signal amplitude. And we'll also see dB scales used to specify the response of filters. So for example, this plot is on a log-log scale. The y-axis is given in decibels, and you can see here what the linear values are that those correspond to. And for this particular Butterworth filter, we have a minus 3 dB point of 0.01 pi, so notice that the plot intersects minus 3 dB on the y-axis at that point. This filter is a second-order filter, so it has a roll-off of 12 dB per octave, which says that every time the frequency doubles, the amplitude goes down by a factor of 12 dB, or about a factor of 4 in linear terms. That's the same thing as saying that the filter has a roll-off of 40 dB per decade. In other words, if the frequency increases by a factor of 10, the amplitude of its response decreases by a factor of 100. So decibels are very useful, and you might want to get in the habit of implementing your amplitude controls in decibels rather than in linear scale. And I'd like you to try that now. In the sine slider project, change the amplitude, so instead of using a linear scale between 0 and 1, we use a decibel scale, and I suggest that you make this go from minus 40 dB to 0 dB, where 0 dB corresponds to a linear amplitude of 1.0. You have a couple options of what you could do with a slider. You could either use the map function to rescale its range, or you could simply change the values for the minimum and maximum inside of setup. In either case, you're going to need to implement the formula to go from dB to a linear scale. And my hint to you is that the POW function, or POWF, which is a slightly more efficient version using single precision floating point, will implement this useful equation x to the power of y. See if you can make this work. Pause the video here. Alright, here we are back to our sine slider example, and this is the critical line that we want to change. Right now this is done in linear amplitude between 0 and 1, and I'm just going to take the simple way out, and I'm going to change the range of the input to be between minus 40 dB and 0 dB. And let's give it a default value of minus 20 dB, let's say. Okay. Now here, when we get the amplitude from the slider, it's going to be a number between minus 40 and 0. We do not want to multiply the output by a number between minus 40 and 0. We want to convert the decibel scale into a linear scale before we can perform this multiplication. So let's try that. So first of all, I'm going to change this variable from being called amplitude to being called amplitude dB. And the reason that we do that is just to make sure that we don't accidentally use the value of amplitude and multiply it here even though it's still expressed in decibels. And then I'm going to make a new float called amplitude, and this is going to follow the equation that we saw on the slide. So I'm going to use the POW function, and it's going to be 10 to the power of dB divided by 20. So amplitude dB divided by 20.0. Oops, just like that. So if we run this now, we should find that we have not a linear scale, but a decibel scale for our amplitude. Okay, so if we go over to the GUI, here we are, we can see that the amplitude is expressed in dB rather than in linear scale. And what you should find is that as you adjust the amplitude up and down, it is a much more perceptually smooth change in volume as opposed to it being much more sensitive near the bottom of the control compared to near the top. Now you might hear some clicks here. Sort of zipper noise as we increase and decrease the slider. Where does that come from? We'll look at that kind of thing later on, but this has to do with the value of the amplitude suddenly jumping between one call to render and the next, which leads to a discontinuity in the signal. What we've seen thus far is how to manipulate parameters in both a linear and a decibel scale. What we're going to see in a moment is how we can also treat frequency on a logarithmic scale, which is also more perceptually relevant. But first, let's talk a little bit about how oscillators are often implemented in modular synths. It's often quite common that an oscillator module is not in fact just one simple oscillator, but two or more oscillators added together, which might be tuned very closely but not exactly to the same frequency. And what happens is the slight detuning between oscillators results in beat frequencies. The reason for this actually comes from a trigonometric identity where adding two sines together is equivalent to multiplying a sine and a cosine at their sum and their difference divided by 2. So practically speaking, if we want to implement an oscillator module that involves two or more detuned oscillators, we're going to need some more controls. We're going to need one control for the center frequency of both oscillators. That basically is what we already have in our frequency control. But let's also have a control for the amount of detuning between the two different oscillators. What we're going to do is we're going to calculate the frequency of each oscillator according to this pair of formulas. The first oscillator is going to have a frequency of 1 plus r times f, and the second oscillator is going to have a frequency of 1 minus r times f, where f is our center frequency and r is the amount of detuning. If we set r to 0, it just goes back to the previous case that we had with no detuning, but if we set r to something just slightly greater than 0, you'll find that we get a really nice sound out of this. Now I'd like you to try this on the project called Wavetable Slider, which is in the companion materials. The Wavetable Slider example picks up on some of the things that we did in the previous lecture, and it implements a sawtooth oscillator using a wavetable. The nice thing about a sawtooth oscillator is that it has a lot of very rich harmonics, so when we combine detuned oscillators you get a really nice phasing effect between them. So this task is a bit of a longer one. What you need to figure out is not only how to add another GUI control for the detuning ratio, but how to duplicate the wavetable oscillator. You need to figure out which bits of the code need to be duplicated and which ones do not, so that you can have two separate sawtooth oscillators which are mixed together with slightly different frequencies. Pause the video here, see if you can make two detuned oscillators adjustable from the GUI. We'll look at the code together in a moment. Well, first of all, here we are in the basic wavetable slider example, having not made any changes yet. You can see that we have the amplitude expressed in dB, as we looked at before, and that is converted to a linear ratio using the POW function. The frequency comes straight from the slider, and there's only one oscillator in this example. So if I run this, you'll hear a relatively straightforward sawtooth wave, and we can adjust that here in the GUI. Fine. Now let's make this more interesting by having two detuned oscillators. Here's my first step toward a solution. Notice that I've added a slider, which I call detune. It has a default value of 0, or no detuning, and the valid range is between 0 and 0.05. So that's about one semitone in either direction. You'll find that the most interesting part of the range is probably the bit that's just right near 0, but not equal to 0. And we have our amplitude calculated in dB like before, the frequencies being used to gather the center frequency of the two oscillators, and we're gathering our detune value here. Now the crucial calculation is this one, where the first frequency is 1.0 plus detune times the center frequency. The second one is 1.0 minus detune times the center frequency. Now what happens then is in the for loop, we can see that actually all of this code that was doing our linear interpolation from the wavetable is just duplicated. I've just basically copied and pasted the same bit of code once after the other, the first one using the first read pointer and the second one using the second read pointer. So let me take a pause there and talk about what needs to be duplicated and what does not. I'm going to go to the top of this file and you'll see that there is still only one wavetable. We still only have the need to save one version of the sawtooth, but we do need to save two separate read pointers because we have two different oscillators going at different frequencies. And so that's what I've done. I've changed it to be called gReadPointer1 and gReadPointer2. So if I go back down to the render function at this point, you'll see that we are using gReadPointer1 here, and we had to use that consistently throughout there, update that according to frequency 1, and then the second time we had to use gReadPointer2. Notice that in the first time I declare these variables as type float, but I don't redeclare them as type float in this case. We only need to declare the variable once within a particular scope, and in fact we can only declare it once. If I put a float here I would get an error. The other thing to notice is that this time, when I calculate the second oscillator, I'm mixing its value into the first oscillator. So I already calculated out up here. This is for the first oscillator. And then for the second oscillator, I just say out plus equal to the calculation for my second oscillator. So that mixes the two of them together. And then I finally write the sum of them here to the audio output. So this will work. We can try this now. If we run the project, it will build. And we should be able to hear that when we adjust the detuning ratio, that we get some really nice phasing effects between the two oscillators. When we start, we don't hear anything, but that's because we haven't actually increased the detuning yet. Now if I change this here, you can hear some nice phasing going on. So that's already a lot richer than what we had before. That said, this is really not very good code. It does work, but we've relied on a lot of copying and pasting of code, and this is just asking for bugs. Because if we forgot to change the name of one of these read pointers, or we copied and pasted something wrong, or we made a change later on, it would be very easy for this code to fall out of sync. There are some better ways of doing this than having multiple copies of variables with different names. The most obvious way to approach this would be to use an array and a for loop. So let's look at an example that looks like that. Okay, here's an example implemented with some better coding practice, although potentially a little bit harder to understand the first time you see it. You can see that for the two oscillators, we have not two different variables for the read pointers, but we have one variable which is an array with two elements inside. And this notation here with the curly braces says initialize both of the two elements of the array to 0 when we start. The bits inside of setup are largely the same as they were before, but the bits inside of render have changed a little bit. So here we can see that we have an array of two different frequencies, and we calculate the first element of the array as being the first equation we saw before, the center frequency times 1 plus detune, and the second element of the array as the center frequency times 1.0 minus detune. What this lets us do is write a for loop inside of a for loop inside of render. What's happening here? Well, the first of these for loops is the one that we've seen a number of times before. It steps through each of the audio frames within the block. Within that for loop, there is a different for loop, and this is stepping through the total number of oscillators. In this case, we start with oscillator 0, and we keep going until the oscillator number is equal to 2, and we stop at that point. In other words, we run this loop twice, first with a value of 0, then with a value of 1. We don't run it with a value of 2 because 2 is not less than 2. Inside of this inner for loop, then, we place the linear interpolation code that we saw before. We can see that it's using G-read pointers, index I within the array. And the same idea with frequencies, index I within the array. The benefit here is that we only have to write this code once, and it can just run as many times as we have number of oscillators. We had to move this value outside of the for loop so that it persisted beyond the end of the for loop, and what we're doing is we're starting it at a value of 0, and then each iteration through the for loop we're mixing in the value of that oscillator. Finally, we write the output to all of the audio channels. So if we run this code, we should see that we have largely the same thing, but implemented in a nicer way. Going over to the GUI, turn some detuning on, and change the amplitude. And we can see that we can change the frequency. Now here's a curious effect. Suppose I change the detune back to 0, and then I do it again, and again. What's going on here? Why does it sound different each time it goes back to 0? Well, the answer is that we have two different oscillators of different phases to one another, and as long as the detune is non-zero, the two oscillators will drift in phase with respect to one another, and that's what gives this nice phasing effect. But when we bring the detune back to 0, the two oscillators are going to lock in phase, but potentially at a different offset depending on what phase they happen to be when we set the detune back to 0. Next up, let's talk about one of the most important parameters in music, which is pitch, which is related to frequency. It happens that human pitch perception, like amplitude perception, operates on a logarithmic scale. What this means is that musical intervals that we're familiar with, like octaves and fifths and thirds, are defined as ratios in frequency rather than any fixed offset measured in hertz. What this means is that if we're given a frequency and we want to figure out what note on the keyboard that represents, we would need a logarithmic computation to get there, and conversely, to get from a note on the keyboard to a frequency, we would need an exponential calculation. We've seen that the decibel scale is one way to get between linear and logarithmic scales, but for frequency we tend to use a different calculation. By convention, the A above middle C is tuned to 440 Hz, though you'll find small variations on this depending on the context. One octave above this A corresponds to twice the frequency, which is 880 Hz. What that means is that we have 12 piano keys, or 12 semitones, that make up a doubling in frequency. And if we plot frequency versus the key on the keyboard, we can see that the frequencies get larger in an exponential fashion. You'll see in the x-axis here a scale called MIDI note, and this is a convention we'll talk about in a moment, but basically it's a way of giving each key on the keyboard a unique number agreed between different devices, and by convention middle C on the keyboard always has a value of 60. More on this in a moment. What we're interested in here is converting from a pitch or a note number to frequency. In other words, we want to say for a particular key on the keyboard, how do we find the frequency associated with that note? And the idea should be that an increment in pitch should always correspond to the same musical interval, regardless of whether it started out as a high note or a low note. There are various approaches to this. In the case of analog modular synthesis, we'll often use something called a control voltage, or CV, to control the pitch of our oscillator. And there's a common standard known as 1 volt per octave, and the idea is that if the frequency goes up by 1 volt, the oscillator should go up by an octave. In other words, the pitch should go up by a factor of 2. What that means mathematically is that given a reference frequency, fref, and an input V, which is measured in octaves, then we can calculate the output frequency based on this formula, fref times 2 to the power of V. So for example, if the reference frequency was 100 Hertz and we wanted to go up 2 octaves from that, we would have 100 times 2 to the power of 2, which is 100 times 4, which is 400 Hertz. That's 2 octaves higher than 100 Hertz. The next question is, what if our variable V was measured in semitones instead of in octaves? There are 12 semitones in 1 octave, so we need to find a way to convert from semitones to octaves. The way to do that is relatively straightforward. We just divide it by 12. So our new expression takes V measured in semitones, a reference frequency fref, and produces an output frequency fout. So for example, if our reference frequency was 100 Hertz, and we had V was equal to 12 semitones, then we would have 100 times 2 to the power of 12 divided by 12, that is 2 to the power of 1, so we would have fout is equal to 200 Hertz. What this gives us is the ability to specify a number of semitones as an interval above some reference frequency, and then to convert that into a frequency in Hertz. Now see if you can implement this equation into the wavetable slider project. The idea here is to change the frequency slider so that instead of giving you the value directly in Hertz, it's going to give you a value in semitones. And let's take a range of 0 to 24 semitones. And this is going to represent an interval above a reference frequency of 110 Hertz, which is 2 octaves below A440. So in other words, we are going to have a frequency range which goes from 110 to 440 Hertz, but we're not specifying that directly in Hertz on a linear scale, we are specifying that on a musical semitone scale. And what you'll find when you do this is that the slider becomes much more uniformly sensitive across the pitch range. The same amount of variation in position of the slider will always correspond to the same musical interval. Try this now, pause the video here. Okay, here's our answer. It's largely the same as the previous example we looked at, with just a couple changes. First of all, instead of specifying frequency in Hertz, I'm specifying a pitch in semitones. Again, 0 is equivalent to the reference frequency, and then the semitones indicate the interval above that reference frequency. So the default value here is 12, the range is 0 to 24. Here I get the pitch from the slider inside the render function, and then I need to do another calculation to turn this from a semitone value into a frequency. That calculation you can find here. This implements the equation that we saw in the slides. So here's our reference frequency, 110 Hertz, and then here we have the power function, pow(f), which is taking 2 to the power of pitch divided by 12. Again, that's because we had pitch measured in semitones. By dividing by 12, we convert it into octaves. Then we take 2 to the power of the number of octaves, multiply it by the reference frequency, and then we finally get our result. So if we run this project, we'll find that it sounds about like before, but our pitch control is much smoother. Let's add some detuning. And now I can change the pitch. And so we can see that the pitch control is roughly uniformly sensitive across its entire pitch range. It's much more intuitive to work in this space of semitones than it is to work in Hertz if you want to start implementing musical intervals. A moment ago we talked about something called MIDI note number. Let's talk about what this means. You'll probably have heard the term MIDI before. It stands for Musical Instrument Digital Interface. It's a standard protocol for communicating between controllers like keyboards and synthesizers. It's been around since 1983, widely implemented in the industry, and relatively few updates until very recently when the MIDI 2.0 standard was released. MIDI, in its original 1.0 incarnation, defines a note number for each key of the piano, and these are numbered sequentially from low to high, with the convention that middle C is always note number 60. What that means is that the lowest key of the piano works out to be 21, the highest C on the piano is note number 108. The A above middle C is note number 69 by the same count. What else we know is that the A above middle C has a frequency of 440 Hertz, and these two facts are enough to give us a conversion from MIDI note number into frequency. How do we do that? Well, for a given note number n, we can figure out how many semitones it is above or below A440. How do we do that? Well, we just take n and we subtract the note number for A440, which is 69. Okay. How do we then turn that into a number of octaves above or below A440? We'll take n minus 69 and we'll convert semitones into octaves by dividing by 12. There we go. Finally, if we know that note number 69 corresponds to a reference frequency of 440 Hertz, how do we calculate the frequency for a note number of n? Well, then we get this equation. Fout is equal to 440, our reference frequency, times 2 to the power of n minus 69 divided by 12. This is our standard equation which we use to convert MIDI note number into frequency. You will find this used in all sorts of different audio software. Another useful feature about working with MIDI note numbers is that each integer value of n is going to correspond to a familiar frequency of a piano key. What that means is that if we just limit n to being integer values rather than floating point values, we can very easily get a chromatic scale. Of course, it's also entirely possible to use this equation with fractional values as well as integers. The easiest way to test this in our GUI example is just to control this parameter called increment, which we found at the end of the setup function. Remember that when we added a slider, we gave it a name, we gave it a default value, a minimum and a maximum, and then the increment tells us essentially what is the granularity of change that is allowed. We could set it to 0 to mean a continuous range with no quantization. That's what we've done thus far. If you set it to a value of 1, you get a chromatic scale in this case. Or you could set it to some other value to get microtones. For example, 0.5 would give you quarter tones. Let's hear how that sounds. Here, the only change I've made is changing the increment of the pitch control from 0 to 1. So you'll see that if I run this project now, when we adjust the pitch, now we're operating in semitones rather than in continuous frequency. One last thing for you to try, which we won't go over here together, is what to do if you wanted to have a different musical scale for your control besides a chromatic scale. Most commonly, we might want to control pitch within a diatonic scale. Diatonic scales include the standard major and minor scales, and they characteristically have 7 notes to the octave with a very particular pattern of intervals between them. The problem that we have here is that there's no single increment value we could put into our slider to ensure that we had a diatonic scale, because some notes are closer together than others. So what should we do instead? One approach that you might consider would be to use an array as essentially a lookup table for pitch values within the diatonic scale. So for example, if you wanted to have a 2-octave C major scale, you could use an array to hold the MIDI note numbers associated with each element of the scale. Then what you do is you use the control from the GUI as an index into the array, rather than using it to calculate the value of the frequency directly. So this is something that you can add relatively straightforwardly to the example that we just looked at, but we won't look at it here together. We will, however, return to MIDI in a later lecture. That's it for this time. As always, don't forget to subscribe to us on YouTube so that you're notified of each of the new lectures as they become available. In the meantime, you can follow us on social media at Bela Platform, or drop by our forum, our blog, or our knowledge base at learn.bela.io. Thanks very much for tuning in. See you the next time.